All right, everybody, let's start the lecture. This is a course on differential privacy, and today is our lecture 14. And we finished the chapter on differentially private machine learning, and today we're moving into a new chapter on data-dependent differentially private algorithm design. And how do we do things that are specific to each data and design formally differentially private algorithms that exploit the properties of the data to improve your utility. Okay, so we'll start with a recap of the last chapter of the course. So we talked about differentially private machine learning and on the several different models. So we started by talking about the learning theoretic treatment of private learning by considering a finite hypothesis class, right? So we wanted to find the best policy within or the best classifier within a finite set of classifier on and so as to approximately minimize empirical risk, and that implies learning by the standard uniform convergence argument. And we've seen that in private learning we can minimize the excess empirical risk with order proportional to the log of h and n epsilon, where epsilon is a privacy parameter and n is a number of data points, and h is the size of the hypothesis class. And this is typically faster than learning in a non-private non-private setting. So we have a pretty satisfactory result over there. And on the other hand, whenever we move into an infinite hypothesis class, we cannot just replace this log of cardinality of the hypothesis class with the other complexity measure as easy as we are able to do it in a non-private setting. So in particular, so in the non-private case, we can replace this log of h cardinality with a VC dimension. But even for the case when the VC dimension is equal to 1, there exists cases where private learning is just impossible for any possible epsilon smaller than positive infinity. And the same lower bound hold for epsilon delta dp in any non-trivial regimes for delta. So it's really a problem of the incompatibility of differential privacy as a definition and the learning problem when we want a uniform rate of convergence as number of data point goes to infinity for all distributions simultaneously. Okay, so for the infinite class, not privately learnable. So then we restrict our attention to loss functions that in some sense is Lipschitz, right? So when the loss functions are Lipschitz, it changes slowly according to movements of the parameter, and when the loss functions are Lipschitz, then we are able to we're able to generalize the hypothesis class from the finite class to infinite classes, we studied this on the several model. We started by talking about posterior sampling and how it is connected to exponential mechanism, and then use the asymptotic analysis from classical statistics to understand how it works in practice. And when the number of data points is large, but that's not really computationally efficient in some cases because sampling from the posterior distribution is sometimes challenging. So we move on to talk about the convex empirical risk minimization problem. And in these problems, the individual loss function that we're trying to minimize is assumed to be a convex function, right? In this case, the posterior sampling and exponential mechanism is sampling from a so-called log concave distribution, and that becomes computationally efficient. Moreover, there are a breadth of other algorithms that we can consider. So in particular, using the tools from convex analysis and convex optimization, we can design algorithms that enforces a global sensitivity of the argmin of the optimal solution that minimizes empirical risk to have bounded sensitivity. And so we can simply add noise using Gaussian mechanism or Laplace mechanism to those learned coefficients using output perturbation. And the slightly better algorithm that leverages the convexity and the optimality condition is through the so-called objective perturbation. So this is when we add a synthetic linear loss with a random data point that's drawn from some probability distribution. For instance, let's draw a Gaussian random vector with appropriately chosen standard deviation of the noise for every coordinate, and then we add this B drawn from, say, Gaussian multivariate Gaussian or the isotropic multivariate Gaussian, and then inner product with a parameter that we're optimizing over. So this perturbs the objective function, and we through the optimality condition and by a change of variable trick, then we were able to show that this mechanism also satisfies differential privacy. And in the case of generalized linear model, it's given us very satisfactory result in the sense that it obtains the best possible solution for all possible algorithms out there for these problems. But objective perturbation is suboptimal for the general smooth learning problems, and it also requires a smoothness and cannot easily handle the constrained cases when the parameter theta needs to sit within a predefined constraint set, and that motivated us to consider an even broader algorithm. And the tool that we used is the iterative algorithm called gradient descent and stochastic gradient descent. And by simply adding noise to the gradients or the stochastic gradient, that gives us just a composition of Gaussian mechanism. Or in the noisy stochastic gradient descent case, we're also adding noise, but then before we compute the gradient, there's a random sampling procedure to obtain the mini batch. So the mechanism of interest is a subsampled Gaussian mechanism, right? And the noisy gradient descent is just this composed by t iterations, and the noisy stochastic gradient descent is just this composed by t iteration, and the sampling ratio, like we used gamma to denote the probability of sampling ratio. Yeah, so we've done a pretty thorough analysis of the convergence of this algorithm to their optimal solution, measured in terms of the suboptimality of the empirical risk or the objective function. So how much worse that your differentially private algorithm would return, the solution that your differentially private algorithm would return, measured in terms of the objective functions that we're trying to minimize, comparing to the actual arg mean that we can obtain in the non-private setting. So we've seen that in terms of the excess, so-called excess empirical risk, the noisy gradient descent and noisy stochastic gradient descent, they are both optimal algorithms when their parameters are chosen correctly, and the regime for them to be optimal is when you add large noise in every iteration and you make the learning rate very small, and then you also make the number of iterations proportionally larger. Okay, so that's the that's what we learned about noisy gradient descent and noisy stochastic gradient descent, and their comparisons are shown in this figure, which we went over extensively in the last lecture. So we can see that all of these bound like matches what is achievable by GLM by objective perturbation in the generalized linear model, under additional assumptions, and therefore, like, these are essentially the optimal rates that we can get. Like, this was formally proven as an information theoretic lower bound in the reference paper in our reading list, Basili et al. And noisy SGD and noisy gradient descent also have the additional benefit that we can analyze it under additional settings, such as constraint setting, strongly convex setting, and non-convex setting, and so that we can obtain detailed utility analysis for each one of these settings. And the catch of noisy gradient descent and noisy stochastic gradient descent is that they are somewhat more computationally inefficient, because the optimal results are obtained at the limit when the number of iterations go to infinity, right? So, and each iteration for noisy gradient descent requires a full pass of the data set, and each iteration of the stochastic gradient descent requires a lot smaller, but the number of iterations still needs to be very large in order for the algorithm to converge to a good solution. We did a computational analysis of these two algorithms in the last lecture. So we've seen that the number of the computational complexity measured by the number of incremental gradient costs. So this is the one evaluation of the gradient of one particular data point, right? So if we treat that as a constant time, then these are the total number of these are the computational complexity of these algorithms for achieving the information theoretic limit up to a constant, like in big O notation. So we can see that generally noisy SGD improves over the noisy gradient descent. The catch, a small catch, is that noisy stochastic gradient descent requires using subsampled Gaussian mechanism, which privacy analysis is slightly inferior comparing to that of the Gaussian mechanism. And this leaves the open problem: what is the optimal computational complexity for any algorithm that can be used to obtain the information theoretic limit under these various settings? Yeah, so clearly, like, maybe we'll have to go beyond the family of gradient descent and iterative algorithms like this in order to break this n square like barrier, say, on these settings. And then there was a paper that I pointed you guys to in the last lecture. The last part of the previous lecture was about deep learning with differential privacy. In this setting, we don't really have too many tools that are available, and the only popular and the only in some sense like somewhat practical algorithm is a noisy stochastic gradient descent, but with a per example gradient clipped within each mini batch. So the way that you implement noisy SGD in the deep learning setting requires a per example gradient clipping to control the L2 global sensitivity of the stochastic gradient query, because otherwise like the theoretical bound for the Lipschitz constant for deep neural network is just too large for the estimate of the Lipschitz constant to be of any interest to practical applications. There are basically two threads of research in this domain. So one is an empirical question. So what are the practical tricks and additional information and additional cues that one can exploit to improve noisy SGD on various learning problems, and then obtaining better and better results on standard benchmarks in computer vision, in natural language processing, and so on. The other interesting question theoretically is that like how do we understand gradient clipping in training? So I've shown you one slide last time about the effect of gradient clipping in generalized linear model, which is equivalent to modifying your loss function by robustifying your loss function a little bit through defining a piecewise Huber function, like robustified loss function. Like for any of your favorite your favorite generalized linear model, you can by gradient clipping, you are essentially modifying the loss functions. So you are actually optimizing some correct objective function, but it's just a different objective function comparing to what you wanted to optimize to begin with. But in general, in the non-convex case, and gradient clipping has a significant effect, and as it introduces biases to training, and sometimes it leads to non-convergence or conversion to very suboptimal points. And another thread in deep learning with differential privacy is to assume having access to some additional public data. So this is a setting that is picking up and gaining momentum, and we've seen a lot of successful applications of having access to only a small public data. Like sometimes a big public data, in other cases, a very small public data, and you can substantially improve the privacy utility trade-off in the application of interest. And in particular, towards the end of the last lecture, we talked about two family of algorithms. One is called the private aggregation of t-training ensembles, or PATE. The other is called private k nearest neighbors. So these are algorithms operates in this knowledge transfer setting when we have unlabeled public data. And the idea is to use the private data to somehow create synthetic labels for these unlabeled public data. So once we privately release these synthetic labels, then we can just train like our model completely on the public domain. And this has the benefit of not having to worry about the inner working of learning algorithms. So it sometimes allows us to take any black box learner that will generate predictions and then just like pull them together and then as teachers so as to label these public data. So there are some theoretical analysis on PATE on this knowledge transfer setting. So I went over this slide very quickly in the last lecture because we were running out of time. So let me highlight. Yeah, the big table is a bit intimidating to look at out of context, but let me highlight a number of interesting aspects of these results. So first of all, what are these notations? So D denotes the VC dimension of the problem. So recall that previously any like when these classes are say VC classes, even if D is equal to 1, then there are no private learning algorithm. What this implies is that when you have a tiny bit of public data that are available, you can actually learn all VC classes without losing too much of a rate. So in particular, M is the number of data points that's available in the public, and N is the number of data points that you need from the private data set, and this is the suboptimality that you can get. So you can see that so it goes to 0 at a 1/m rate, which means that suppose we want to achieve alpha accuracy, it requires only D over alpha public data point, while it requires, say, I guess it requires D over alpha to the some outer tau number of data points in order to so you need a substantially larger private data set than the public data sets. To say it differently, so if we augment a large private data set with just a tiny bit of public data, then we can already convert something that's not learnable at all into something that's actually learnable. And PATE is also a very practical algorithm. And from the left column to the right column, it's described different versions of PATE. So again, PATE tries to leverage a bunch of teachers and use these teachers to annotate public data points. And what this sparse vector technique based PATE, what it does is that it automatically adapts to situations where teachers will agree very substantially with other teachers. So in that case, this SVT based approach essentially do not need it does not need to pay any privacy budget to release a correct label when the teachers agree with large majority. With large margin, and you only need to pay a price for releasing those labels if the teachers do not agree mostly do not agree with each other. So in this case, it's sparse vector technique but applied in a very specific way. So under this setting, the rates can be improved, and in the realizable case in particular, now we are getting now we are getting like 1/n rate for the private data as well. So this is almost as good as the realizable learning in a non-private case, because in the non-private case, in the realizable setting, the rate is 1 over like d over n. Now it's d to the power of 1.5 over n. So if you treat d and epsilon to be a constant, then effectively you don't lose anything. Yeah. So a big open problem is that whether the same story can be said for agnostic learning with a practical efficient algorithm. So it is known that even in the agnostic setting, there exists like an unimplementable algorithm that essentially do some kind of exponential mechanism that leverages a small amount of public data that achieves the information theoretic limit for the agnostic setting, and you actually learn almost as fast as in the non-private setting for constant epsilon, but yeah. By far, there isn't any algorithm that's known to date that are able to learn agnostically. So agnostic and realizable means that whether there exists a perfect classifier within the class, right? So whether H star can perfectly classify all data points, and if there doesn't exist such a H star, then it is a agnostic setting. Otherwise, it is a realizable setting. Right, and this noise model called Sibakov noise condition is just something between, right, which allows you to have classifiers that are not perfect, but still it behaves somewhat like the realizable case. Okay, so that's all I wanted to talk about, like in a differentially private machine learning. So we'll get back to this problem after we introduce some new tools in the upcoming chapter about data-dependent differentially private design, algorithm design. Right, so this lecture is going to be about how do we go beyond the worst case, and how do we design algorithm that doesn't rely on, say, the worst case sensitivity. And so we'll talk about the technique called smooth sensitivity and give a running example of releasing the median of a sequence of numerical numbers. And then we'll also cover some more recent results on smooth sensitivity in a recent 2019 revisit of this problem. All right, so here are the reading materials for today. So this is a really classical paper for differential privacy, which introduces a smooth sensitivity and subsampling and aggregate scheme that enforces a smooth sensitivity for any type of queries. And this other paper, average cases averages, are like this paper is a more recent revisit for the idea of smooth sensitivity that derives the rainy DP and concentrated DP analysis for many smooth sensitivity based noise adding algorithms. Okay, so it's been a while, so let's maybe get back to the more basic stuff rather than thinking about machine learning. So let's get back to just differentially private query release. So as an example, we've been focusing on linear queries, which say this query of a data set X has a form of a statistical average of all individuals in the data point. So let's say that your data set X is X1 to Xn. Okay, for this lecture, let's consider the add. Let's like throw away the add or remove neighboring relation, but just consider the replace one neighboring relation, so that n is public, and we are doing replace one neighboring relation. So what is a neighbor of x? So the x prime will be, say, let's replace the last element of this data set with xn prime. Okay, so that's a setting that we're going to be consider, and then we are saying that dxx prime being smaller than k means that the Hamming distance between these two data sets is k. So in this case, when they are neighbors, k is equal to 1. Okay, and when they differ by two data points, then k is equal to 2, and so on. Okay, so this is a form of a linear query. So it's still somewhat restrictive, even though we can use this to do a lot of things. Say calculating the stochastic gradient, we can use this to calculate the average income, and so on. But this is still somewhat restrictive. We want to be able to handle more complex query classes, and sometimes this query class doesn't really satisfy like a bounded sensitivity. But for this, let's review what are the tools that we've learned. We've learned this noise adding mechanism. This mechanism A takes dataset X and output, say, Laplace noise with a parameter being the sensitivity of this F over epsilon, or the Gaussian mechanism, which adds Gaussian noise with to every coordinates with a parameter with parameter I guess sigma square, and this is known to satisfy epsilon differential privacy, and this is known to satisfy the L2 sensitivity square over 2 sigma square concentrated differential privacy. Right, so these are our analysis of this algorithm. And so what are these deltas? So the global sensitivity, global L1 sensitivity is just defined to be the max over all neighboring data sets such that they differ by at most one element. And then we calculate the L1 perturbation of this query F when we alternate when we alternate between the two neighbors. And similarly, L2 sensitivity is just the same, but with the norm of this being the Euclidean norm rather than the L1 norm. Okay, so I'd like to highlight that these sensitivity measures are global because we are taking every pair of neighboring data set in order to obtain this upper bound. So this quantity, whatever it is, needs to hold that it needs to be a valid upper bound for all pairs of neighboring data sets. So sometimes this is quite bad. So I'll give an example of that by defining the median query. Right, so you all know what a median is. You sort the sequence of numbers, you pick the one in the middle. So that's a median. So let's say the data set is again is x1 to xn. Let's say that this data set, they're all scalars, and each one of them, xi, belongs to some bounded range from 0 to say this capital lambda, and for simplicity, let's also assume that n is an odd number, so we don't have to define like a median when there are like 2 points that could both be median. So when n is an odd number, then let's sort this data set. And then it gives us the order statistics x1, x2 to xn, right? And so let me actually write this thing in the middle. So 2 n plus 1 over 2 xn, right? So when I have these brackets, they denote the order statistics. So later I may just drop these brackets because like we can always sort this data set and then represent it in a way that's ordered from the smallest to the largest. But these are the mathematical notation for the so-called order statistics. Okay, so this is a median. The number in the middle is a median. So we define this median query, which takes the data set. So let's call this X. That takes this data set by just outputting x n plus 1 over 2. Okay, so now this is a valid query, right? It's one data access, and we use this all the time, like in databases, in preliminary data analysis to understand what the regular behavior of each attribute would look like. So what is a global sensitivity for this query? So I'll give you an example. So let's say that we have n being potentially large, but then this is our 2n plus 1 over 2's element. So this is the median. And then suddenly I jump to lambda. Okay, this is again a sorted sequence of the data set. So this is our data set. But so let's say that we are now like just changing one of the elements. We can modify this into a neighboring data set. So we'll just modify any of these zeros, right? So if we modify any of these zeros, then we'll end up changing the median. So the sorted sequence will end up becoming like we can actually change it to lambda. Okay, so now this is a median. To say it differently, there exists a like somewhat pathological data set such that the difference between this median query is as large as the largest possible. It's as large as the bounded range, right? So suppose we apply Laplace mechanism or a Gaussian mechanism to release this number, right? So since it will hide any information within the bounded range, then it's not going to give us anything meaningful, unless we take this epsilon to be way larger than 1 and cheat. But yeah, any meaningful privacy would mean like a substantial reduction in the utility for getting this median query. So global sensitivity is not going to work for this problem. At least it's not going to give us a sufficiently high utility at a reasonable range of epsilon parameters. Okay, so let me give you another example that we've already seen. Say linear regression. So what is linear regression? So basically we try to minimize this theta parameter by adding the noise, by adding up the square loss. So the square loss of this individual data points square. So that's linear regression. And this is equal to, just if we use matrix representation, x theta minus y Frobenius norm square. Okay, and well, we know that the closed form solution for this on dataset xy is just the ordinarily square. And suppose we add one data point to x and y add I guess one data point to the label, then in the alternative world, this linear regression will return just a slightly perturbed version of this original objective function. X is n by d, So yeah, so I think there's a transpose here. Okay, yeah. So this is adding, but since we're doing the neighboring relationship being replaced one, so we'll need to add and also remove something. So we also have to remove the corresponding. But let me ignore that. So basically there's something that got added to this covariance matrix that we invert. And then so we've seen from previously that in the output perturbations privacy analysis that without making any additional assumptions, like x theta star and theta tilde star can be arbitrarily far away from each other. So this happens when x transpose x is nearly singular, and there are some directions that you happen to add this x transpose there. Right. So when you do that, then suddenly there's a big component in this theta tilde that doesn't really exist in theta star, and then the global sensitivity can be unbounded. So the global sensitivity is unbounded in general. Right. So what is the approach that we used from earlier? It is to regularize, right? Suppose we regularize by adding this additional regularization term so that the problem becomes strongly convex. Then we can then using the definition of using the definition of strong convexity, we can show that this is smaller than this is smaller than the Lipschitz constant over lambda. And what is the Lipschitz constant here? The Lipschitz constant of the individual loss function. We can just take the gradient of this individual loss function, which gives us xi and the residual xi transpose theta minus yi a factor of 2, right? So the Lipschitz constant will be the boundedness of the X space square multiplied with the boundedness of the theta space that we're optimizing over, or at least theta star, the smallest value that we can set. Yeah, so basically some constant on top. So in order to make this somewhat small, we actually have to make this lambda like very large, make lambda increase with n, and that was how we obtained this 1/square root of n rate earlier. In practice, however, when we consider a practical application of linear regression, in most of the cases, these X are designed by the people who run experiments. And by design, some of these X satisfy the properties that is more well conditioned, so that we can get a good estimate of this theta with narrow confidence intervals in all the coordinates. In other cases, when X is randomly sampled from some distribution, if your feature is selected appropriately, then this X should also be somewhat well behaved. So global sensitivity approach does not really take into account of the fact that let's say that if X transpose X, so this is a matrix in D by D, and it's also a positive semi-definite matrix. Suppose it is strictly positive definite, and in addition, it is lower bounded by some alpha parameter times n times identity, right, with some constant alpha. Then we know that the whole objective function, even without this noise adding, is already strongly convex from the data set itself, right? So from there we can derive that the perturbation is smaller than lambda X transpose X itself with this Lipschitz constant on top. So rather than we have to add this additional regularization, and that could help to obtain like much stronger convergence bound and much with much smaller sensitivity as we've derived, right? And in the noisy gradient descent and noisy SGD case, we know that this is a strong convexity of the problem is actually helping us to converge faster to the optimal solution and obtain like a smaller information theoretic limit for the private learning. So global sensitivity is not able to exploit the fact that the nice property of the data set itself. They are similar to the median case. Right. So that brings us to the idea of how about we weaken the definition of global sensitivity into something local? When we consider the sensitivity can be conditioned on this particular input data set X. Right, so very similar to the global sensitivity definition. So this Q is just a query which I was denoting with F earlier. So the local sensitivity is a largest perturbation. It's the largest perturbation of this Q when we maximize over all possible neighbors, right? So when we enumerate over all possible neighbors of my particular data set, how large this perturbation is. right? So yeah, I guess I'm missing the absolute value here also. So as an example, in median, so what does local sensitivity look like in median? So let's say that we have this order statistics x n minus 1 over 2, x n plus 1 over 2, x n plus 3 over 2, all the way to xn, right? So let's say that you have this data set. And now this is a particular data set. So instead of depending on, instead of having the global sensitivity that depends on some hypothetical worst case data set that's very like ill behaved, in the situations when the like when we have this actual data set, like the maximum perturbation by adding or removing, by replacing one of the data points. So can anyone tell me that what is a way of modifying this data set by just one entry such that it changes the median, right? So again, this is a median. This is a sorted sequence. This is a median. What is like the worst possible way of modifying the data set such that the median would move to largest extent possible? Anyone?
Modify the median itself.
Okay, how would you modify the median itself?
To either the value smaller than that or the value larger than that, such that the distance is the most.
Cool. Yeah, you can move this median anywhere you want, right? So you can, for instance, make this median like lambda, or make this median 0. Right? You can make this data point. But then what's going to happen is that like if you move this above the immediate immediate like data point that's just slightly larger than you, then this one will become the median. Right, so you can move this anywhere by inserting this anywhere to the right-hand side, and then this becomes median. On the other hand, if you change this median such that it move over here or anywhere here, then this becomes a median. Right, so no matter what you do, like you can arbitrarily change any data point in this data set. So if you change, like what happens if you don't change this median? What happens if you change all the other things? But it's also not going to substantially affect the medians. Let's say you change this x1 and then move it to somewhere between these these three numbers in the middle, then you could change the median. But no matter what you do, like the changes to the median, it's got to be bounded between between like these two numbers, right? So in particular, the local sensitivity of the median query is equal to the larger of just two things. The larger of xn plus 1 over 2 minus xn minus 1 over 2 and x n plus 3 over 2 minus xn plus 1 over 2. This is the largest possible perturbation to the median. You can, which can be realized, as Kai-Chi nicely pointed out. So we can simply move this median around, like between these two boxes that sandwich it in between. And in practice, when you have a much denser data point that's around this median, then the local sensitivity can actually be quite small. Okay, so I'll I guess leave it as an exercise to people who are interested in this to show that suppose all these points are drawn from some normal distribution, and what is a local sensitivity on the what is a local sensitivity on the median, right? So you'll see that it'll behave very similar to that of the mean. So similarly, like when we consider linear regression, what is a largest perturbation that we can get on this particular data set. So again, theta star is equal to x transpose x inverse x transpose y. Right, so you can still bound it, right? You can still bound it, and based on our calculation earlier, so the local sensitivity really would look like this. So this is actually the local sensitivity of linear regression, because now you are allowed to condition on this particular data set. So the local sensitivity is able to exploit the is able, yeah, and by the way, from this assumption, and this is alpha times n. Right, so this is the smallest eigenvalue of x transpose x. So it will become the L over maybe 2L times the smallest eigenvalue of x transpose x. So that would be the local sensitivity of this linear regression query. And again, so this could be orders of magnitude smaller comparing to its global sensitivity, where this lambda mean of x transpose x is arbitrarily close to 0. So a natural idea is that can we just add noise proportional to local sensitivity rather than the global sensitivity, right? So that would be the most practically relevant thing to do, right? If my data set is behaving well, and I should just add noise that's proportional to locally, like how much differences I have against any other neighbors, right? So that should protect me against the detection of like that should sufficiently obfuscate the output such that the two distributions are indistinguishable, right? So since everything is local and local sensitivity is an upper bound of any of my neighbors from me, so it turns out that there's some big issue in this approach that makes it like not differentially private at all. So let's illustrate this with an example from the median again. So let's take this example of the median. We'll go with this example. So let's say we have sorted sequence of the data set 0, 0, and 2, 0, 0, 0, lambda, and lambda. Okay, so that's the data set. And now, this is your median. Like order 2, I guess n plus 1 over 2. Okay, so what is the local sensitivity for this data set? Anyone? So based on the formula that we had in the last slide, it should be pretty straightforward to see. Yeah, so the local sensitivity, so let's say this data set is X. So the local sensitivity of a median query on this data set is 0. So let's now consider a neighbor data set. So which is 0, 0, 0, 0, and now I'm replacing this 0 with lambda. Now this is a median. Yeah, first observe that like f of x equals to 0 and f of x prime is also equal to 0. So they are exactly the same. But what is the local sensitivity for x prime? Anyone? Yeah, it's the largest possible. Yeah, excellent. So it is lambda. So what would you do? Suppose you calibrate your noise, say add a Laplace noise with a scale parameter proportional to the sensitivity over epsilon, right? Suppose you add noise of Laplace and local sensitivity over epsilon. Like what is the behavior of these two data sets? So in the first data set, since the local sensitivity is 0, you will not be adding any noise at all. In the second data set, since the like local sensitivity is the largest possible, then you will add a very large noise. Right? So this doesn't even have to be lambda. Let's say that this is 0.001, right? And then the local sensitivity here will be 0.001, right? It's sufficiently close to 0. But suppose we plot the two distributions of interest on so this is 0 on A of x, so this will be a point mass. On the other hand, for x x prime, so A of x prime, it will be a Laplace distribution, something like that, around this f of right. So I argue that you can distinguish these two probability distributions with like perfect accuracy. Right. So yeah. So basically, if you get the answer being exactly 0, you argue that it is coming from data set X. If it is not at 0, it can be anything. Then you output that the data set that's coming from X prime. Right. So this is not differentially private for any parameter epsilon delta. Yeah, so something like this was actually implemented in the real world. So motivated by the GDPR in Europe. So this is general data protection data protection regulation in Europe. The people try to come up with practical database query tools to satisfy some notions of privacy. And they even went all the way to say that this is GDPR compliant. And what they did is to like selectively add noise or to adjust the noise variance according to what is the nature of the query and how sensitive it is. And they implemented a bunch of different heuristics so that they empirically tested their method against many known attacks to the database systems, including those that tries to steal your data and those that try to do data linkage attack and many others. So like based on the experiment, it seems pretty reassuring, but precisely because they are using this kind of data dependent noise adding, and in some cases the amount of noise that you add can change quite drastically from one query to another. And that allow people to create attacks of a very similar format to what I mentioned just now. A few years ago, there was this paper written, so how to break Diffie's sticky noise, and by exploiting the signal in the noise itself. So basically, the variance of the noise itself contains information about what the data set is and how you can extract information from this data set, and they've given a pretty detailed description on how to break this seemingly very strong protection tools that's Diffie has implemented. Yeah, so it's a very interesting story. So if you're interested in this, like you should take a look at this blog post and also like maybe take a look at this paper itself. So the short answer is that, well, adding noise according to local sensitivity is not really a good idea, because and the underlying reason behind that is that the local sensitivity itself might be insensitive, might not be stable. So local sensitivity itself might be unstable, and because of that, the noise that you add at neighboring data set can actually reveal very drastic information about what could happen. On the other hand, like this calibrating noise according to local sensitivity is behind our idea of wanting to design something that's data dependent, right? So if we're doing things that are data independent, we're only adding noise according to global sensitivity that's completely oblivious of the actual data set that we have. That defeats the purpose of data dependence data-dependent differential private mechanism design, right? So the key idea is to somehow replace local sensitivity with another quantity that's more stable, and then calibrating noise according to that. And we're still trying to calibrate noise according to local sensitivity, but only as much as possible while satisfying some stability constraints on the amount of noise that we add. Right, so that leads to many different approaches in data-dependent DP algorithm design, including smooth sensitivity, which is the topic of the remainder of today's course, and proposed test release, and how do you privately bounding or releasing the local sensitivity, and also in this category, I would say that those stability-based query release are also which like has an interesting feature that it doesn't require any noise added, any noise to be added to the query. So all of these are one way or another trying to adapt to local sensitivity using ways that are stable, either through the changing the sensitivity and then the amount of noise you add, or through the stability implied by differential privacy itself. Okay, so yeah, let's talk about the first approach, and arguably the most elegant approach called smooth sensitivity. What is smooth sensitivity is defined through the local sensitivity. So smooth sensitivity is an upper bound of the local sensitivity. So what it does is that you enumerate over all possible data sets in the data universe, and then you take a look at how far away this data set Y is from your input data set in terms of the replacing how many data points do you have to replace before X becomes Y, right? And then you calculate the local sensitivity at this this chosen data set, and but then you make it exponentially smaller according to how far away that you are from the current data set. So, and there's a parameter beta. So we say that this is a beta smooth sensitivity. If this like it is defined by this, and beta governs how quickly that you go to zero, how fast this decay is as you move away from your current data set. So let me illustrate this a little bit, maybe graphically. Let's say that the horizontal axis, this is the space of data, right? So let's say that your input data is here. Okay, and let's say that your sensitivity, I guess your sensitivity is this large, right? So I guess the vertical axis is a local sensitivity, or smooth sensitivity. They're all put to the on the same. They are all comparable, right? So we can plot them in the same figure. And well, so if we move this a little bit away from X, so this is X prime, such that X prime and X is equal to 1, right? So over here, this is X double prime, so dx double prime X is equal to 2, right? So let's say that this is where, and on the like horizontal axis, I'm just enumerating like in general, this is not just like a univariate thing that we cannot simply plot it on a line like this, because there are multiple ways that you can get neighbors. So you should think about it as you move away from X, and this becomes the maximum of all the possible neighbors. But as you move away from X, then I guess the horizontal axis, you can also view it as a dx prime of X. So then this will be 0, there will be 1, this will be 2, 3, and so on. Okay. Let's say on the left, we can also make this 1, 2, 3, just to say there are like two data sets that are away from you. And for each one of these dots, then we can calculate their local sensitivity. So let's say that this X prime has a local sensitivity that looks like that. This one has a local sensitivity that looks like that. And this one has a local sensitivity that's also small, but this one, it has a local sensitivity that's somewhat large. Okay, and this one, yeah, we can calculate the arbitrary local sensitivity, sensitivity measure here. And these are the local sensitivity corresponding to all like each and every data set in the data space, right? So what does the global sensitivity, what does local sensitivity look like? So the smooth sensitivity would say that, so we'll do a bit of smoothing at every single location by decaying this according to how far away other data set is from me, by saying that I'm creating an upper bound that goes from here to, that decays using something like a Laplace distribution shape, right? I'm doing this. And on every little one of these, I'm drawing this smooth upper bound. At the end of the day, the final smooth sensitivity that you get, all of this will be the point-wise upper bound of all of these. For instance, what is a smooth sensitivity of this point? It's exactly here. What is the smooth sensitivity of this point? It is here. What is the smooth sensitivity of this data set? Is here. And here. So you basically take anything that's given on this envelope. So that's the smooth sensitivity that you get. So ultimately, when you draw this smooth sensitivity, you can see that in some cases it is equal to the local sensitivity. In other cases, it is larger than the local sensitivity. Like for instance here, right? And what you end up getting is just a smoothed version, and it remains an upper bound of the local sensitivity, but it is smoothly changing by this exponential function according to this in the definition, right? So this colored thickened color red is a smooth sensitivity of this input data set X prime. Okay, so let me modify the color. Yeah, I hope this illustration is helpful. So let's maybe take a look at this property like before we go to our break. So smooth sensitivity satisfy something called a smoothing property, right? So there are two properties that's natural from the definition itself. First of all, the smooth sensitivity is larger than the local sensitivity for any data point X. The second is that for any neighboring data set of this X, then the smooth sensitivity of your data point is smaller than smaller than the smooth sensitivity multiplied by e to the power of beta, like from any of your neighbor Y, right? So this is called the beta smooth property. Yeah, so we'll show that the smooth sensitivity that we construct earlier satisfy this beta smooth property like now, and then we'll go to our break. Okay, so there are two properties that needs to be established. The like since this is defined as this, it is naturally an upper bound of X. So we can simply take Y to be equal to X, and then that gives us an upper bound, right? That gives us that checks the first condition. So this is pretty straightforward. So we'll now show that the smooth sensitivity by definition also satisfy like the second smoothing property. so let's first construct something called so first of all, so the y is a neighbor of x, and secondly, let's construct this x prime such that the smooth sensitivity of f beta at x is x prime is equal to the local sensitivity of f at x prime and e to the power of minus d x x prime. Okay, let's see. This is okay. So I think this should be the smooth sensitivity of x is equal to sure. Now let's show that this is always true. So we'll start with the smooth sensitivity of y. Okay, the smooth sensitivity of y is I guess by this definition, the smooth sensitivity of y is since y and x differs by just one data point. So this is larger than well since y yeah, let's say that we'll apply the this clause by choosing this x to be y, and then by choosing this this y to be x prime, and then we can show that the smooth sensitivity of y is always larger than e to the power of minus beta distance between y and x prime. Okay, and using the fact that x and y differs by at most one coordinate, and the fact that there's a triangular inequality for this Hamming distance, then we can further show that this is lower bounded by, so this is L is local sensitivity, and e to the minus beta and d x prime I guess minus beta. So I'm making this even smaller. I'm making this possibly even smaller, and by just adding one to the sensitivity, which is the maximum number of perturbations. Suppose I replace this y by x, and the next using the fact that by our definition, this x prime is the one that is obtaining the one that achieves the argmax, right? So we are making this assumption that we are taking this particular x prime such that x prime is the one that attains the argmax. So they're equal sign. So these two together, if we take this e to the power of minus beta out, what remains is the local sensitivity of L prime multiplied with e to the power of minus beta d and x prime. And this is equal to e to the power of minus beta, the smooth sensitivity of x by definition, right? And then if we move this beta to the other side, it recovers this property. Yes, question.
So like why does the smoothness of y larger than the local of x prime due to the negative? Like where's the first one?
The first inequality. Okay, so the first inequality is coming from the definition of smooth sensitivity. So S of y, this is it's equal to the maximum, right? And I can put the right hand side to be a ls ls of x prime e to the power of minus beta d x x prime y, right? So since this is maximum, then I can say that for any such x prime, this is larger or equal to.
So x prime is by construction.
X prime is something arbitrary, right? And we construct this particular, yeah. So for any x prime, the first inequality is true. Yeah, just by the definition of smooth sensitivity.
Okay.
Right, and then we're taking this x prime to be something specific, such that equal sign is true for the last step. Okay, so this shows that the smooth sensitivity satisfies the beta smoothing property, and as a matter of fact, the smooth sensitivity is the optimal bound. It's the smallest possible upper bound that satisfies this smoothing property. So I will not prove this to you. So I'll leave this as an exercise, and maybe I'll ask you guys to prove this in a last homework question. But the idea is that you assume there is the other S that satisfies the smoothing property, and then you show that this S is always smaller than is always bigger or equal to this particular S star, right? Which demonstrates that the smooth sensitivity is really the right upper bound to use because there are no other upper bounds that are that are better than this particular one. All right, and we'll go through our break, and then we'll come back and talk about what are the type of noises that we need to add in order to use the smooth sensitivity to achieve like differential privacy. Yeah, so we'll resume in 2:20. All right, let's continue with the lecture. So just now we've shown that the smooth sensitivity satisfies the beta smoothing property in the sense that that I can upper bound my sensitivity with just the e to the power of beta blow up. So the intuition behind this is that like what makes the local calibrating noise to local sensitivity so bad, and that's because like when I move my when I change my data set by just one data point, and the local sensitivity can change from 0 to some positive number, to some very large number. And suppose this is satisfied, suppose the we impose this additional constraint on the amount of noise that we add, then this says that across the two neighboring data sets, the amount of noise that we add also needs to change only a little. Like the maximum amount of the noise that I change, suppose I calibrate it according to the smooth sensitivity, is gonna change by at most e to the power of beta. Right. So when beta is small, so that's changing the variance only a little. Right? So that's why smoothing is useful. And the next question obviously is what are the admissible noise that we can add according to the sensitivity in order to achieve differential privacy, right? So there are two properties that this noise that we need to add needs to satisfy. So let's say that we're adding this noise z with a certain probability distribution, and there are two properties that needs to be satisfied. So one is a sliding property or translation property, which says that which says the following equation that inequality that you should be somewhat familiar with already from the differential privacy epsilon delta differential privacy definition. But before that, let me formalize what I mean by this adding a particular vector to a set, right? So we use this notation to denote that we're just translating every single element within this set. So let's say that this S is a box, right? So what let's say that this is our delta. What this does is to take every point here and move towards this direction, and take this here to move towards this direction. And then this dashed set is this is S plus delta. This is what we define, like how we define this this notation. And now how do we multiply like a quantity to a set, right? So let's still take, say this is a set S. Let's say this is origin. Say multiplying so e to the power of lambda to S means that we are multiplying this to every element in this set. So this makes this set a little bit bigger. Say if lambda is larger than 0, so I'll take this point for example, and scaling this by e to the power of lambda will make it a little bit bigger here. But scaling this point a little bit bigger will make it proportionally larger, right? So what's going to happen is that if we dilate or multiply this set by a constant, then the set itself is going to get bigger. So this is S times e to the power of lambda. This region. Yeah. So that's how I define multiplying and adding to a set. Basically, it's element-wise operation. I'm doing that for every single element in this set. And the sliding and dilation properties simply says that the noise needs to satisfy that when you shift it a little bit, when you shift the noise a bit by delta, and then for any set that you can consider, it is the difference is captured by this hockey stick divergence. Okay, and similarly, the dilation property says that if I change the scale parameter for the noise by multiplying that by e to the power of epsilon, so I'm basically changing the scale parameter. So in the Gaussian case, so this is a Laplace case. So this will be, say, Laplace 1 versus Laplace 0, 1 versus Laplace 0 e to the power of lambda. So they are both centered at 0, but the scale parameter differs a little bit. Yeah, I hope that this sufficiently illustrate this. And why do we need the say the variance of the Laplace distribution or the scale parameter of the Laplace distribution to be different? Why do we need this dilation property? And that's precisely because we are calibrating the noise to something that can change when we modify the data set a little bit. So we want to add data dependent noise. We want to add slightly larger noise for data sets that are more well behaved and has smaller local sensitivity, and add a bigger noise when the data set has larger local or smooth sensitivity. Right, so that requires us to also capture the well-behavedness of the noise up to like a minor change to the scaling parameter. Okay, and the mechanism is really just noise adding. So whenever this noise satisfy alpha sliding property and beta dilation property, then adding noise with the magnitude proportional to the smooth sensitivity over this alpha parameter satisfies epsilon delta dp. And this alpha and beta, they are parameters that we can choose according to your desired epsilon and delta privacy budget. And for different noises, and there are different formula to calculate this alpha and beta parameter. Okay, it gets like slightly more complicated than the global sensitivity analysis, but yeah, it should be intuitively like, yeah, you should intuitively understand like why dilation properties is required and needed for this problem. So let's now like show that these are the properties that are needed for the differential privacy guarantee to hold. Okay, so again, like we want to show epsilon delta differential privacy, and by definition, it requires us to show that for any pair of neighboring data set, and also for any output subset of the output space S, this inequality is true. Plus I guess plus delta. Okay. So let's see. So we'll start from the left hand side. We'll start AX in S, and let's substitute what AS looks like. So this will be just f of x. This is our query plus the smooth sensitivity over alpha multiplied with this noise random variable z, right? So this belongs to this set S, and we can move things around by writing this as a set about this noise vector z. So this says that this z belongs to I guess S minus fx and divide by smooth sensitivity and multiply with this alpha parameter. Okay, so this is a set up to this translation and scaling property. You first translate it, and then you scale it by a factor of alpha over Sx. So that's defined like just now, and everything is well defined. Well, I argue that we can now apply the translation property. We can now apply the translation property by getting this inequality. So now this is z belongs to a s minus fy over sx. Okay, so how we shall understand this? So this is a plus half delta. So how we should understand this? So basically we can add f of y and subtract f of y over here without changing this set, and then we can group this f of x and the difference between fx and fy together. So that what is the translation to this set? So let's see. The translation to this set is a times fx minus fy over sx. Okay, so that's the translation. That's the translation that we add to this setting of interest in order to obtain this set. Okay, so how large is the translation? We know that the dilation property, we know that the sliding property is applied to all such delta such that delta's one norm is smaller than alpha. So we can take the one norm here. So we can take the one norm here, and this is equal to a and fx minus fy one norm over s of x. But what is this? This is bounded by a local sensitivity of x, since y is a neighbor of am I using x prime or am I using y? Yeah, so let me use x prime. So since x prime is a neighbor of x, the numerator is smaller than a times local sensitivity over the smooth sensitivity, and smooth sensitivity is an upper bound of local sensitivity at x. Therefore, this is smaller than a. This is smaller than I guess alpha, and for this, it checks the condition that this is smaller than alpha. Therefore, we can apply the sliding property, and that's how we obtain this inequality. Okay, this is how we get this inequality. Okay, so the next thing to do is to replace this sx with sx prime, because that will help us to recover the distribution. Suppose we add noise to the neighbor data set x prime. Okay, so what we're gonna do is to first rewrite this e to the power of half epsilon and p z belongs to s sx prime over sx and multiply with a s minus fx prime over s of x prime. I'm basically multiplying sx prime and divide s of prime, right? So I'm basically multiplying and dividing the same quantity, and then move this s of x in the numerator out. So I argue that this is the same plus half delta. And now, like, this is just a scaling of a particular set, right? So this is a scaling of a particular set, and then we can apply the dilation property. We can apply the dilation property if we can check that this ratio between s prime and x is bounded by e to the power of lambda. But what is this sx prime over s of x? By the smoothing property, by the smoothing property over here, then we know that whenever x and y are neighbors, then we can bound their differences. We can bound the ratio by e to the power of beta, right? So this is smaller than e to the power of beta, and if this is smaller than e to the power of beta, so notice that this applies for all lambda that are smaller than beta. To say it differently, this scaling factor, this scaling factor, so let's say that this is equal to e to the power of lambda, and this lambda absolute value is smaller than beta. For this reason, then we can apply the dilation property and then recover e to the power of half epsilon and I can simply drop this, and this will be alpha s minus f plus half delta. And this, if I just move things around, I can multiply this x prime to the other side and then move things around, and this simply becomes e to the power of half epsilon, e to the power of half epsilon, the probability of fx prime inside S plus half delta plus half delta is equal to e to the power of epsilon p fx prime inside S plus e to the power of half epsilon plus 1 delta, right? So it's not quite what we wanted to yeah, it's not quite what we wanted to prove, but it's pretty close to what we want to prove. So basically what we end up proving is that there's a delta prime, and delta prime is equal to this half delta plus half delta e to the power of half epsilon, right? So it's for small epsilon, these are more or less the same, but for like large epsilon, there's an exponential blow up on the delta parameter. So what I'm showing you is that this is very similar to group privacy. So it's like you are changing the distribution twice, one by dilation and the other time by translation. So this is essentially doing the group privacy type of analysis. So this kind of additional blow up on delta is in some sense needed. Like and this is also how the proof in the paper works, but their results, I guess, stated is slightly incorrectly. But yeah, the whole argument of applying the two properties to obtain epsilon delta dp will stay valid. Okay, so is this argument clear? So so I'm applying the two properties by choosing this set to be something specific, and then that allows us to decompose the proof of this inequality into two steps. And in each step, I apply one of the property. I apply translation first, and then I apply this dilation property. All right, so to give you some idea on what are the admissible distributions, so Cauchy distribution, Laplace distribution, and Gaussian distribution there. So the familiar Laplace and Gaussian noise, they are both admissible, like with some parameter choice, alpha and beta parameter, So one is better than the other, and they are both given as epsilon delta dp. So when we allow delta to be non-zero, and then adding Laplace noise and Gaussian noise, both works. So we can't add it to a local sensitivity, but we can calibrate this noise according to smooth sensitivity. Yeah, for the high dimensional case, it's a little bit trickier, and the calculations are a lot more complicated. But for the univariate case, these are methods that actually work reasonably. Suppose we want to get the pure differential privacy, then we can add even heavier tailed distribution than Laplace distribution. So Cauchy distribution is a family of distributions that's heavy tailed. So basically, when there's a parameter gamma, so that controls the power law of the Cauchy noise. When gamma is larger than I guess when gamma is equal to 2, then the distribution doesn't even have a mean, right? The mean is unbounded. And when gamma is large, then say larger than 3, then both the mean and the variance, they exist. But the higher order moments does not actually exist. But with a heavy tail distribution, it creates the more well-behaved, more concentrated privacy law distribution of the privacy loss random variable. And interestingly, with more concentrated noise that you add, the privacy loss random variable will become more heavy tailed. And which is good and bad. So there's always a trade-off. And interestingly, for Gaussian noise, so we know that the distribution of the noise that you add and the distribution of the privacy loss random variable is somewhat special, and they're both Gaussian, and they have the same heaviness in their tails. But for Cauchy noise, we can get, you can see that this alpha and beta parameters, they depend only on this gamma choice on the probability density, and then on the epsilon parameter. So this actually gives us a pure DP with delta equals to 0. Yeah, the next thing that I want to demonstrate is that for the problem of median that we start our discussion with, we can actually compute the smooth sensitivity, because the formula for smooth sensitivity is such a crazy formula that requires us to enumerate over all possible data sets. So this is infeasible in most cases. And how do we compute this in practice? So one way to do this is to decompose this maximization into true maximization by first conditioning on the number of, by conditioning on specific value of this dx comma y. Okay, so what's inside this bracket is that whenever, so we enumerate over all possible data sets that differs by k elements from our input data set. Then I find the largest possible local sensitivity, and sometimes this is easy to calculate. And if this is easy to calculate, then the maximization becomes a maximization just over a finite number of elements, right? So I should enumerate over different choices of k, and then multiply that by e to the power of minus k, and then I compute the pointwise maximum. So one possibility to make this computationally efficient is to say that, this f actually has a global sensitivity that's not too crazy, right? So in the median case, the global sensitivity of f is smaller than lambda, right? So as you move away from your data points, and as k gets larger, then you can upper bound this by, say, the max of k from 0, 1 to, say, to some realistic number that we want to calculate, say m, and m is much smaller than n, then I can get e to the power of minus k epsilon, and max y dxy is equal to k lsf of y. So this is something that we can calculate. So if m is small, and then I can take the max of that with the with e to the power of minus m plus 1 epsilon multiply with just the global sensitivity, right? I can clip this so that I can handle any k that are larger than m by just the trivial global sensitivity bound, because the global sensitivity bound always applies. So this helps us to say, well, when there is a conservative global sensitivity, like this can make this global sensitivity exponentially smaller, and also adapts to those data points that are nearer to you. So this could help you to calculate smooth sensitivity upper bound by just truncating the search. For median, actually, we can do something a lot better. We can actually calculate the smooth sensitivity exactly using this formula. So here's how. Yeah. So because let's say that we have this sorted data set x1 to xn, and we've seen that the local sensitivity is really the maximum of two values. So basically pick xm in the middle, go to the left and go to the right, and then check your distances, and then take the max of the two distances. And then the question is that how can we calculate this quantity? So how can we efficiently enumerate the data set that are k steps away, right? So I argue that this is like really about how we can enumerate data sets by trying to modify k points, right? So if we try to modify just 1 point, then we can jump 1 hop. If we are allowed to modify two data points, then we can jump at most 2 hops, right? For k data points, we can jump k hops. So what is this saying is that we have x1 to xn and x m minus k plus 1, xm, and then to xm plus k plus 1. So basically all we can hope to modify is one contiguous sequence that's between m minus k plus 1 to m plus k plus 1 to m plus k, because anything that's outside this boundary is out of our is outside of our reach, and we cannot hope to by just modifying k data points and modify the median such that they're larger or smaller than this or that. Okay, so because of that, we can simply try searching for this t parameter and then find the contiguous sequence that gives us the largest possible jump between one point that are between any 2 points that differs by k point. Because if that is the case, then we can modify this data set to achieve this local sensitivity with a data set that is at most k away from my current data set x. Right, so this is computationally efficient. You can solve this by enumerating all possible t, and this is order n. And then in the outside, this is another order n. So in total, this is order n squared. So you have an efficient algorithm to polynomial time algorithm to compute the smooth sensitivity. So if you use like some slightly fancier algorithm design, you can reduce this to n log n, like through dynamic programming. Yeah, not differential privacy, but dynamic programming. And the details of this fancier algorithm is in the paper. Okay, so as a checkpoint, so I've talked about smooth sensitivity. So the idea is that we cannot really calibrate noise according to its local sensitivity, even if it is great, even though it is great, and we can somehow smoothen the local sensitivity by construct a smooth upper bound. I guess, and those noise distributions that satisfy the translation properties and scaling properties are admissible, and then we can add these noises according to the smooth sensitivity that we can compute for the particular query. So in general, it is computationally inefficient to compute smooth sensitivity, but for many cases, including the median, we can compute it. And for other cases, even if we cannot compute it, we can somehow obtain like a very good upper bound of the smooth sensitivity, so we can add noise accordingly. Yeah, I have some additional slides on the concentrated differential privacy, so I'll go over them very quickly before we end today's lecture. So more recently, like this problem of smooth sensitivity was revisited, and Mark Bong and Thomas Stanke, they came up with a bunch of other noise that one can add. And these noise, in addition to the epsilon delta DP guarantee, also satisfy the concentrated differential privacy. So again, CDP is an upper bound of the Renyi differential privacy with a single parameter. So it's a linear upper bound. So this leverages the sub-Gaussian properties of these privacy loss random variable. So the noise are actually quite simple. So we can generate this noise that we add to the query according to smooth sensitivity by a product of two noise. The first noise x is drawn from a Laplace distribution, and this y is drawn from just a Gaussian distribution. It's called log normal because the log of e to the power of this y is a normal distribution. So we can we understand that the variance of the variance of this noise z is 1/3 of e to the power of 2 sigma square. So it's nothing too crazy, and it also satisfies the concentrated differential privacy with parameter being a half square of this. Which is nice because then we can compose this with other mechanisms that we know, the Renyi differential privacy and concentrated DP. So as a summary, so far we've learned a bunch of things. So we know that for Cauchy distribution, we can get pure DP, and Thomas and and Mark, they further show that if you draw from the student T distribution, so this is something that's easy to sample and has a lot of application in statistics, you can get the pure DP. And for the Laplace log normal and the uniform log normal or some other transformation of normal by applying the hyperbolic sine function to the normal random variable, you can get the rho concentrated differential privacy. And from the original paper, we know that adding the more classical noise that we learned, that gives the approximate epsilon delta differential privacy guarantees. Okay, so I'm gonna skip the proof for the concentrated DP, but I'll make some remarks at the beginning of the next lecture. And then I'll also tell you a little bit about the practical performances of these new like log normal distributions that you add according to smooth sensitivity to some interesting real life applications. All right, so more to come in the next lecture. I'll see you guys next Monday.